And this is why we were able to solve those problems the other day by this method.
Okay. And this is connected to the other stupid solution too?
The other what?
The other one? Like the extension of general equations?
Well, I mean,
This is the idea though?
this essentially takes the idea of, in some sense, it just generalizes the complex. I mean, the motivation for this section is all about, you know, this guy.
Yeah.
So it's like, okay, well, I'll work with, you know, I'm going to work on an algebra such that k squared plus 1 equal to 0, and I take e to the kt, you know, and so that's 1 plus kt, 1/2 k squared t squared, and so forth and so on.
Yeah.
And so after a little bit of math, that gives me 1 minus 1/2 t squared plus 1 over 4 factorial t to the 4th plus dot dot plus k times 1 t minus 1 over 3 factorial t cubed over 5 factorial t to the 5th. And of course, you can recognize these have names. That's cosine t and that's sine t. So by this theorem, these are the special functions of the extension algebra for this differential equation, therefore they form a fundamental solution set. But in fact, this example was the motivating example for this whole method. What's just so kind of shocking about it to me is that it just as well solves something like, you know,
Like the basic?
like this one, you know? You're looking, so you're like, well, I just want k cubed equal to 0, so I look at e to the kt, which is going to be 1 plus kt plus 1/2 k squared t squared. And then everything beyond that is 0 because it truncates. And so that says y equals to like c1 plus c2t plus 1/2 c3t squared is the general solution because those are the 1/2 t squared special functions of that algebra. I think it's cool.
No, I'm not saying it's not cool, I'm just saying that like, I was just connecting both of them.
So yeah.
So what are the now problems with ODEs that we have?
Right.
Because now that you have general solutions for every case of, you know, whether it's a zero divisor or not, now what's your goal with these ODEs?
Oh, I do have some stuff at the end of this that I combine this with the isomorphism stuff to like use the exponential and stupid algebra, let me just tell you, theorem 5.22, if I have an isomorphism from A to B, then the exponential of isomorphic algebra is related in the natural way. There's a formula there in theorem 5.22 for that. So when I was knee-deep in this, I found that was something I wanted to do, to understand examples. That's why that's there. Yeah, so there's some more examples here. Oh, example 5.26 circles back to example 5.8. That's that d minus 1 times d minus j acting on a to equal to 0 problem. This is actually kind of a scary looking example, isn't it? Like
Which one?
example 5.26.
to scroll, you have to do 2 fingers. But if you scroll like slightly diagonally to the left, it'll like go back a page. So like I get back to the archive. I'm just like, I have to go straight down. I did it twice. Two six. I just did it again. Okay. Oh, you got a different thing though. You didn't get for. You didn't get that before, right? That solution set.
I know. I'm still looking at 5.26. So like,
That's not. Yeah.
let me write up on the board here.
Yeah, we got.
Right on the board.
Oh well. No, well. I think you just wrote it differently because I think you said you could do this in ascension cosh.
Oh yeah. Well, I claimed there that they're in fact basically the same solution. Just they can be. There's a linear dependence amongst the solution set, which is not to say that they're exactly the same solution. It's just to say that like you can create the same general solution using the results we found before in 5.8, or what we're about to look at in 5.6, but I think it is a good example to show that the stupid solution is not as stupid as you might think, just looking at these elementary examples that are, born of real differential equations. Although I am fond of those examples, because, anyway, so so the differential equation is P of D is what? D minus 1, D minus J, which is D squared minus 1 plus J, D plus J, right? So we're looking at solving P of D eta equal to eta prime prime minus 1 plus J eta prime plus J eta equal to 0. I mean, that's the differential equation we're studying. So the extension algebra technique says you look at e to the, what is it, k, e to the kz, let's say. Well, it says you look at a prime, let's say, which has the form a plus bk, such that a and b are in the hyperbolics, and k squared minus 1 plus jk plus j equals to 0. Right, that's the characteristic equation. So, all right, so then, here a and b, these are hyperbolic numbers, right? This a and b. So e to the kz is equal to, I think I call them, I actually used the extent, See, this is a bit of a pain if you try to do it this way. See, because this is like 1 plus kz, right? Plus 1/2 k squared z squared, right? And so forth. So if I just went on direct calculation, then I would have what? K squared is like 1 plus j times k, right? Minus j. So this would be 1 plus kz plus 1/2. K squared is what? It's 1 plus j k minus j, all that times z squared. All right, so like what's the next thing up? The next thing up that I haven't written yet would be 1 over 3 factorial k times k squared. What's k squared? Well, k squared is 1 plus j k minus j. So it's actually kind of a pain to sort out what happens to these powers of k. See, because like when you get to k cubed, what happens here? You got yourself like 1 plus j times k squared, right? Minus jk. But the k squared is what? The k squared is 1 plus j. So that's 1 plus j squared k minus j minus jk. And, alright, fine, I mean, you can collect stuff. What do we got? So,
1 plus j.
yeah, what's the real part, so to speak? You got 1?
Yeah.
That's not there. There's k here, so forget that. Minus 1/2 jc squared. Right? And over here, I've got a
1/6.
oh, there's a oh no, I gotta look at this one. So 1/6 looks like it's just that.
Yeah. What's up? Plus 1/6?
J.
Or minus?
I
think it's minus.
It's jz to the z cubed, you know. And then plus k times what? Well, k times, well, z.
1 plus j.
Mm-hmm.
1/2. 1 plus j. And then 1 plus j squared minus j z cubed. 1/6. Yeah, no 1/6. Plus 1/6. The 1 plus j squared minus j. Minus j z cubed. J squared minus j z cubed. Okay. Oh, no. Dang it, no.
So, I mean, great. Now, if you go back and look at the example 5.8 and you tilt your head and squint, you might be able to convince yourself that maybe there's a way to take a linearly, there's a way to take, if I call this thing Bob, and if I call this thing Jane, then there's probably a way to take like C1 Bob plus C2 Jane and select other constants, B1, you know, e to the was it JZ? E to the JZ plus B2, Z e to the JZ plus funny function. Because the funny function in example 5.8 is the one that had the 1 plus j.
Yeah.
So like, okay, fine. But you can also see that like the actual computation of arbitrary powers of k here is kind of a pain. And so what I do in example 5.26 is I exploit the and I'm not going to write it out because I'm tired. The isomorphism idea. I say, okay, we'll take the direct product algebra as isomorphic. Oh, wait a minute. No. Incorrect. I look at the characteristic algebra, and I don't say that I do not say that the characteristic algebra is isomorphic to R cross R. In fact, it's not. I say that the characteristic algebra is isomorphic to the null numbers. And the isomorphism is given by 109. I'll write that down, actually. So I'm gonna erase, I mean, my point is like, direct computation of the stupid solution is tenable, but tedious. The technique illustrated in this example is actually much more interesting. So, I say that psi of A0 plus JA1 plus B0 K plus B1 JK, in other words, something like that, is equal to what?
Naught plus A1 plus 1 plus...
A naught plus what?
A naught plus A1 plus 1 plus sigma. What was that called?
Is it this guy?
Yeah, epsilon.
Yeah, it's variable epsilon for what it's worth, but...
Yeah, and times B naught plus B1.
Oh, 1 plus, so it's 1 plus epsilon times.
Yeah.
B what?
B naught plus B1,
Uh-huh.
comma, A naught minus A1 plus...
Comma?
Comma. I'm not going crazy.
Oh, it's the direct product of oh! Psi is from A prime to...
No, yeah.
Okay, so this is the first component of it, and the second one is what?
A naught minus A1 plus J times B naught minus B1.
Interesting. I feel like Nathan found this. I have no memory of finding this. Interesting. So I guess first order of business, if this is right, psi of 1 had better be 1, 1, right?
Yes.
So A1 is 0, A1, B naught, B1 all 0. So 0, 0, 0, 0, 0, so just 1, 1. It's a good sign. And oh, there's the inverse map in there. I was about to say I don't want to calculate. So the inverse map has been graciously calculated for us and provided in equation 110.
Maybe you did do it.
So let's use that formula there, if you don't mind. Like, what is psi inverse of epsilon going to be according to his formula?
Of the equation epsilon?
So this would be, in his formula, x equal to 0, big X equal to 0, big Y equal to 1, big U equal to 0, big V equal to 0, I suppose. I'm curious what the inverse image of epsilon comma 0 is, I should say. So x minus y is 1. No. It's minus 1. It's minus 1. So I've got minus 1 plus j over 2 from the, I'm looking at equation 110.
Yeah, okay.
So that's from the first term. Second term is 0. Then 1 plus j over 2 times y, k. Is that right? I think that should be it, right? In other words, it's 1/2 of k minus 1 times j plus 1. This is the element. So like this should be nilpotent in A prime with order 2. What that means is if we square that element, it should be 0. Because certainly epsilon 0 squared in the, gamma cross H algebra is epsilon squared comma 0 squared, which is 0, 0. So what happens when you square? What happens when you square this? When you get 1/4, right? K squared minus 2k plus 1 times j plus 1 squared, which is 2 times j plus 1, so I'll put a half out here, right?
Yes.
Which is k squared, and let's see here, minus 1 plus j times k. I'm just using
Yeah.
one of the twos, and then I still have a
Wait, wouldn't you have to put a 1/2 in front of the k squared?
plus j, but I'm leaving the half out of, I'm just, get rid of the half, forget the half. If it's 0, it's 0, the half doesn't matter. So, I'm taking, I'm doing the k squared times the 1, right?
Mm-hmm.
And then the minus 2 times this, I'm just keeping that much.
Yeah.
And
plus j, yeah.
the 1 times j plus 1 finds there. And then I still have the plus k squared j. And I still have the sorry, let me write this a slightly different way. So I have
j plus 1's a number. Like that's not a. You can't distribute that, right?
well, j plus 1 k squared, right?
Yeah.
minus 2 times j plus 1 k
Plus j plus
j plus 1. So I get k squared, right?
1. No.
Minus 1 plus j times k plus j. Now at this point, these three terms I'm getting from this one, part of this, and this, but I still have plus jk squared.
Yeah, okay,
I still have plus jk squared, and I still have minus j plus 1 times k, and I still have the plus 1, right?
Uh-huh.
Now, this right here, the reason I did that is because the k squared minus 1 plus jk plus j, this piece is 0, right? This piece right here is 0. So take this. Oh, sneaky. So track with me here. jk squared. So what's j? J times 1 is j, right?
Yeah.
So that's this minus j. J times j, j squared. That's 1. That's this 1 here. So I can factor a j out of this to get that. And then the last one is 1. 1 is j times j. So I can factor a j out like that.
So why did you distribute the k squared but not the 2k? Like you distributed j plus
I'm splitting this into this plus that. The reason I split it is to this plus that is that this is 0.
Okay, but let me backtrack now.
And what I'm about to underline in green is also 0, but it's kind of hidden until you factor out the j. At which point you can see that that's also 0. So there's probably another way to do this calculation, but in fact, if you carefully analyze the that element, you can see that it is in fact an element whose square is 0.
You got a 2, how do you get rid of the 2?
What's that?
You got a 2 in there, like whenever you do it.
Yeah.
Does that just not matter at the end?
The 2, that's why I have 2 j plus 1 k's. See, I took 1 j plus 1 k and I took another j plus 1 k. I wrote them. This term right here,
Yeah.
it goes to this, into that. Minus 2 is minus 1, minus 1, minus 1.
Okay.
So I just split it into those two pieces. Now, honestly, there's probably like a way to like just factor. Look, I'm just probably being stupid about this. Look, like.
Okay, now I got one of the zeros. Okay, so I still have a minus j plus 1. Okay, so I have that left over. I have a jk squared left over, and I have a plus 1 left over.
Mm-hmm.
Okay, so you get. Okay, and then you wait, oh, that's how you factor out a j. Okay, yeah, I'm with you. And then this section you can do.
Oh, see, there's another way we could have done this. 2 times j plus 1 is what? It's j plus 1 squared, right? Are you done with the other one?
Yeah, I found a problem. Oh, that's how you got rid of it. Okay.
Yeah.
Okay.
I mean, that's the first way that it jumped out at me to do it, but here's an easier way.
Okay, and then this is 0 and 0 minus 0, 0.
So if we start with that,
Yeah.
it just occurs to me, I probably can just factor out j plus 1. So I factor j plus 1 out. Okay, squared, that's easy. J plus 1 factoring out of here, you can be careful. I should first notice that 2 times j plus 1 is j plus 1 squared.
Yeah.
So if I notice that that's j plus 1 squared, I can pull one j plus 1 out here, and I can keep the other j plus 1 in here.
Yeah.
And that's just going to be 1. So that's j plus 1 times 0.
No. There's a j up there, not a 1. K squared minus 1 plus j, k plus j. You have plus 1, not plus j.
I guess I should write j here instead. There we go.
What?
Well, that's the messed up thing, is that j plus 1 times j, it's j squared plus j, which is 1 plus j. So j plus 1 factors into j plus 1 times j. Yes. Right. Which is what kept me from seeing it to start with the previous attempt. I know. Yeah. Yeah. So kudos to Nathan for finding this isomorphism, I think. Now my suspicion is what Nathan likely did here is once he had an intuition that it was isomorphic to the null numbers,
Mm-hmm.
I would wager what he did was to solve the equation something squared equal to 0 for a non-zero solution, and he's like, okay, I'm going to call that epsilon. And then he probably solved the equation thing squared equal to 1, and he finally found a solution to that and called that thing j. And then just mapped those things to, epsilon comma 0 and 1 comma j. But anyway, there it is. That example 5.26, man, that's kind of a bear. But it does pop out a fairly nice looking solution in terms of coshs and cinches there. So, and that brings us to section 6. So, I will remind you what we found back at the start of all this was the, can I erase or?
You're good. I'm writing down this solution set.
So the existence and uniqueness problems, basically we have nth order problem, we have n linearly independent solutions. More than that, if you're given initial conditions, n initial conditions for an nth order problem, there exists a unique solution. So in section 6, I show that for degenerate AODEs, all of that falls away. And so I do it by examples. And so a degenerate, Nathan, just puts it out there. Basically, degenerate ODE has the form alpha d to the n plus, q of d. So this acting on eta, where alpha is an element of the zero divisors of A. This is what an nth order degenerate AOD looks like. Now here Q of D is, at most order n minus 1, okay? So, I mean, so let's look at some, basically this section we just look at examples. So it's pretty easy. So toes. Example 6.1, just to give you a sense of what goes wrong here. And this is over the null numbers. All right, you can consider epsilon w prime equal to 0. So to have a solution here, what would it mean? It mean that you can take a derivative with respect to the gamma algebra, right? So you have to assume gamma differentiable. But if f of z is, well, let's say if f from gamma to gamma is gamma differentiable, then w equal to epsilon times f solves epsilon w prime equal to 0, because when you plug it in, you get epsilon squared, right? So this poses considerable discomfort to our fundamental solution theory. This is a first order problem in the degenerate sense, which has infinitely many linearly independent solutions, because you can let f be any gamma differentiable function. And if you want to know what that means, remember that the matrix representation, like a plus b epsilon, what was it? It's like a plus b epsilon, epsilon times a plus b epsilon, right? So that's something like a, b, a, and the epsilon squared is 0, so wait a minute. Yeah.
That was like the hyperbolic numbers just with the...
Well, the 0 there though. So if you compare that to like ux, vx, uy, vy, that says that f equal to u plus epsilon v is gamma differentiable if what? You need ux equal to vy, and you need uy equal to 0. Vx is free, it doesn't matter, whatever it is. So if we have f of x plus epsilon y of the form, let's see here. So I guess I could have like g of x right. If that was my, if that's my, if it's a real function g, then that would give me uy equal to 0, right? And then plus epsilon. So if that's my u, quote unquote, ux. So ux is what? It's dg dx. I need that to be equal to partial v partial y, right? So I just do like y dg dx. Because then partial, if this is v partial y is dg dx. So it solves that, which is to solve this Cauchy-Riemann equation uy equal to 0 is already there for free. And what else can I do with v?
Would be, oh, it can be any constant.
Plus a constant, or plus how about h, which is, as long as it doesn't have any y dependence,
Yeah.
so you can let any function of x go there. So just to give you a sense of what it means to be gamma differentiable, you pick any pair of differentiable functions, h and g, form this kind of pattern, that gives you a gamma differentiable function. How many different choices are there for g and h? There's a lot of choices, right? So, yeah. So this is bad in terms of there's not a fundamental solution set that's finite.
What problems does that cause since it's not finite?
Well, I mean, our general solution is what? It's
C1E.
C1 function plus one-dimensional problem, just C1 times function, right?
Yeah.
So,
Oh, there is.
I mean, you can't characterize the general solution in terms of. Now, there's another kind of solution here as well, right? There's also the solution that's of the form w equal to constant, which isn't necessarily a zero divisor. That's also a solution to this. But anyway, so that's one example. You lose the concept of fundamental solution set. That's kind of a drag. Example 6.2. So we have j minus 1 w prime equal to 0. Now that's degenerate, right? Because it's zero divisor, it's the leading term. And I say, okay, so clearly w equal to j plus 1 times f of z plus a constant solves it, right? So again, we have the problem of infinitely many solutions that are linearly independent. We always have infinitely many solutions, but they're usually indexed by a parameter. But there's more here. Actually, here you can also see a problem of uniqueness. So I said if we can fit, say if you look at w of 0 equal to 0, or w naught rather. Then I said you can fit that with a constant solution. So you can either solve this initial condition with w1 of z just equal to w naught. So that constant solution solves this problem, right? Or you can also do it with w2 of z equal to j plus 1. Z to the n plus w naught. This is a solution to that because the j plus 1 hits the j minus 1, and when you plug in 0, this goes away and just leaves you w naught. But you see, n could be anything.
Yeah.
So these are all solutions to this initial value problem. There's not a unique solution to the initial value problem. Infinitely many solutions to the initial value problem.
So it doesn't even make sense. At least in the real sense.
Degenerate AODs are much weirder. Now, McCoy's theorem 8 indicates a zero divisor in a polynomial ring is annihilated by some zero divisor in the underlying ring. And this algebra explains the structure seen in example 6.1 and 6.2. And it leads us to the following result. If you have a constant coefficient AOD, and it has solutions of the form C times f of z, where C is a fixed constant, and f of z is an arbitrary function in the algebra. That's true if and only if L is a zero divisor in the polynomials in the differentiation operator. What this theorem says is that what happened in the kind of solutions that we gave in 6.1 and 6.2, the existence of such a solution like that it's implying that L equal to P of D is a zero divisor in the ring of the. So this notation right here, this is polynomials in the differentiation operator, and this is the zero divisors of that. So like, for example, epsilon d was an element of the zero divisors of the polynomials over the null numbers of the differentiation operator. Or in this last one, j minus 1, d was a zero divisor in the polynomials over the hyperbolic numbers differentiation operator. Do you need a screwdriver? Oh wait a minute, I thought you were working on the, I heard noises, I thought you were putting them together. She's doing laundry. It's like,
I'm just lifting the heavy detergent.
I misconstrued the noises.
For the proof, why? But this you say C and L must be zero divisors, but why can't C just be zero?
Which part of the?
Oh no, that made no sense. Oh yeah, okay, nope, that makes sense now. I'm on 6.3's proof.
Okay.
Did you? Yeah. This is what you were talking about, right?
I was talking about it, I haven't written it, but
Yeah.
But yeah, it goes back to this McCoy's theorem that if your polynomial is a zero divisor, over the ring of polynomials,
Yeah.
then there exists a zero divisor in the ring of the coefficients, such that C times the zero divisor in the polynomial ring is zero. So it says that zero divisors of polynomials are rather boring in the sense that they have to compare with nil factors, which are constants. Like, it's not the case that you have a zero divisor polynomial which requires a genuine polynomial as its annihilating factor. What do you want to call that? Nil factor or cofactor? I don't know. I have no good name for that thing. The thing that you multiply the thing by to get zero. A certain thingy, as my son often says now. Matthew talks a lot about the certain thingy, which could mean almost anything. Let's see here. Then I say there are also more subtle ways that AOD might be degenerate. For example, 6.4. Does the diagonal scrolling get you?
Yes. I think I remember the page number.
30. let's see here, so this one, I have a differential equation, which is degenerate. But we can actually try to solve it by direct calculation because it's on the direct product algebra. And lo and behold, there's a solution. I'll write it out. So here we have e2d squared plus e1d plus e1 plus e2 acting on eta equal to 0. And so if I let my eta equal to eta 1, eta 2, because we're in the direct product algebra, then this becomes actually eta 1, well, let me say it this way, d, eta 1 dx, the eta 1 dx plus eta 1 equal to 0, and d squared eta 2 dy squared plus eta 2 equal to 0. So we can solve those. Of course, eta 1 equals c1 e to the minus x, eta 2 equals c2 cosine y plus c3 sine y. And so our solution is c1 e to the minus x, comma c2 cosine y plus c3 sine y. And that's the general solution because of the method of calculation just used. So we have seen an abundance, like too many solutions in the fundamental solution set. We've seen infinitely many solutions to an initial value problem, right? Lack of uniqueness. And in this one, we're going to see a lack of existence because if you wanted to have eta of 0, 0 equal to, let's say, 0, 0, and eta of eta prime of 0, 0 equal to 1, 1, I mean, that would be a legitimate set of initial conditions because I'm giving a value for the function as well as its derivative at a given set of the independent parameter, which in this case is 0, 0. What does eta of 0, 0 equal to 0, 0 tell you? It's like C1, C2, right?
Yes.
You plug in 0 into here. And so that implies that C1 equal to C2 equal to 0, right? So what's eta prime? Remember, we differentiate each by x and y, the direct product algebra. So
So that'd be minus C1.
but remember, C1 is 0, so it's still 0.
And then C3 would be minus cosine.
Uh-huh.
No, just cosine, not minus.
Yeah, oh yeah, excuse me, yeah, you're right, C3 cosine y. Now, if eta prime is 0, 0, 0, 0, it's 1, 1 though, right?
Yeah.
So apparently we get C3 equals to minus 1, and 1 equal to 0, hey! Oops. In other words, here you go. This is an initial value problem for which there does not exist a solution. So for a differential equations person, this is the nightmare realm. I mean, you got too many solutions. You got a failure from uniqueness. You've got existence initial value problems which can't be solved unless you choose your initial values appropriately. So. I think theorem 6.5 Theorem 6.5 is a generalization of this example. Like 6.5 actually says if you've got P of D is alpha D to the n plus Q of D, and a Q of D is not a multiple of alpha, then for any zeta naught there exists constants, n constants in the algebra, such that no solution of P data equal to A, P of D on A equal to 0 it fits the initial condition. So like this is not an isolated event. For example, 6.4. Theorem 6.5 says we can rain on this parade. We can rain on every parade of this form. It's horrible. But that brings us to section 7, which is actually something more positive. But we can stop here for a day if you want. It's all good.
I don't want to finish unless you're tired.
Okay. I'm fine. Have you ever looked at Cauchy other problems before?
No.
Ah.
That way, if we have a meeting Thursday or any other day, we can do meetings.
Do what things?
Do new things.
Ah, nice.
Come very far, I'm 3 pages away from the middle section of this template.
So here's a pretty typical x. I'll use t squared y prime prime plus at squared plus bt y prime plus cy equal to 0. This is a typical so-called Cauchy-Euler problem. Now, so I think the first place I saw these was on my my final exam for differential equations, and he's like, consider an equation in this form. Show y equals x to r solves star if and only if r satisfies a lambda squared. It satisfies a particular, an algebra equation. I mean, it was something like this. Or it may have been find the algebra equation that R needs to satisfy to solve this. All right, fine. So what you do is you plug it up in there. So you got yourself an at squared, and then you take the derivative. So differentiate once, you get r, x to the r minus 1. Differentiate again, you get r minus 1, x to the r minus 2. I seem to have switched from t to x. Let's try that again. T to the r. T. All right. So that's the second derivative term, and then of course b t r t to the r minus 1 plus c t to the r. So lo and behold, we got ourselves an a r times r